Okay, I can see it now. Can you all see my slide?
Yes, sir.
Very good. So this is the topic for today. Okay, so it's very important. So you see that so far we were talking about scenarios where two computers connected through some link, they have some data, so let us say the digital data. The digital data will have to be encoded in the form of digital signals to be sent, or digital data can be encoded as um, you know uh, analog signals. So these analog signals are going to have certain carrier components. So the carrier, basically these will act as carriers. So the digital data will be ported onto the carrier signals in order to transmit them. So these carrier signals have certain frequency, which is typically denoted as F subscript C, right? So this is the way basically the transmission of the data from one point to another can take place. So this is something that we have learned. We have learned of schemes like, non-return to zero, return to zero, bipolar AMI, pseudo ternary, digital, Manchester, differential Manchester, right? So like this, actually, we have learned of different schemes. We have also learned of schemes like ASK, FSK, PSK, BPSK, QPSK, right? So we have learned of those schemes basically for sending the data over some signals, whether it is digital or analog signals. We have also uh, basically learned that there might be some errors due to the inherent nature of the channels, right? So the channels are typically noisy, right? So due to noise, due to interference, etc., the data may be lost in transit, right? So even if we are encoding and doing all the things that I mentioned earlier, we might still be losing data. So there are now 2 points. So the receiver should, both the receiver and the sender, right? Both the receiver and the sender should have a mechanism, number one, to detect whether there has been any error in transit, number one. Number two is, if the error is detected, to correct the error, right? So there are error detection mechanisms, right? Like checksum, this parity check, or cyclic redundancy check, right? CRC. So those are some of these different error detection mechanisms. There are also mechanisms for error correction, and because error correction is not in the syllabus, we didn't cover, but there are some error correction mechanisms also. Now, there is another very important thing which also needs certain attention. So whenever we are talking about certain links, right? These links, they are limited in terms of their bandwidths. So we need to use the bandwidth very cautiously, very judiciously. The reason is that basically, so there are several computers, let us say, which will have to talk to several other computers. So one possibility could have been that you run wires between these different computers in all different combinations, right? But obviously, that is a very naive way of doing it, and it's not going to be manageable. So you need some better way to manage the multiplicity in the number of computers which are connected. So if you are talking about one-to-one, there is one level of challenges. But the moment you try to scale up, you are talking about a network where there are multiple senders, multiple receivers. So there, the complexity basically keeps increasing. So we need to really understand that how can we solve this problem? for solving this problem, there are several different ways in which we can do it. So today we are going to talk about something, but there are many other different complexities that are also in place, which we will learn during the rest of the semester. So sometimes it is also required that instead of having very low bandwidth channels run between different computers, etc., you may want to combine these low bandwidth channels to make one channel with a higher bandwidth, right? So this is very important. It is also very important to so let us call this number one, right? So combining some low bandwidth channels to make one link with larger bandwidth, right? So this is one issue. Another important issue is that sometimes the capacity of the channel, the bandwidth of the channel, needs to be expanded in a certain way. So if we do, if we use certain techniques to expand the capacity of the channel, there are certain advantages that we can get with respect to maintaining the privacy of the data that is being transmitted, or for countering certain attacks on the network, which are called jamming. So for anti-jamming, for privacy, etc., we can use certain, bandwidth manipulation kind of techniques, which are typically mathematical in nature, which can help us to expand the bandwidth, right? So there are the first one that I mentioned that can be solved with the help of something called multiplexing, and the latter that I mentioned in the context of bandwidth expansion, in the context of privacy, anti-jamming, etc., that is called spread spectrum. So it is called spread spectrum or spectrum spreading. So you are kind of trying to spread the spectrum. So multiplexing basically tries to combine several channels into one, thereby improving the efficiency of communication. Whereas in spread spectrum, the goal is basically to have enhanced level of privacy, to counter jamming, and so this way basically to improve the overall communication of the system. So in multiplexing, where we are combining several channels into one, there are different types of multiplexing, which I'm going to run you through today. There are techniques called frequency division multiplexing. There are techniques called wavelength division multiplexing. There are techniques called time division multiplexing. So frequency division, wavelength division, time division are some of the different techniques that are going to be covered today. So that's with respect to multiplexing, but there is also something called spread spectrum, as I told you. So in spread spectrum, there are popularly two types of spread spectrums that are used in communication and typically in wireless communication. One is called the FHSS, frequency hopping spread spectrum, and the other one is called DSSS, which is basically direct sequence spread spectrum. Now both FHSS as well as DSSS are important concepts. However, so far both the sections we decided not to cover spread spectrum until some later point in the course, if we can find some time for you, because this course is heavily packed. So for now, the spread spectrum techniques are going to be skipped. So our focus is going to be on multiplexing and bandwidth utilization. So bandwidth utilization with the help of multiplexing is going to be the focus of this course. So once again, what is the bandwidth? Bandwidth basically talks about from the lowest frequency to the highest frequency, how much data can be transmitted over the channel, right? So the maximum amount of data that can be transmitted over a particular link in a given amount of time is what defines bandwidth. So now we are talking about the utilization of this particular capacity. How can we utilize the bandwidth? Okay, so bandwidth utilization basically talks about that judiciously, how can you utilize the bandwidth to achieve the overall goals of the network. Okay, so so one of the ways of achieving this is basically multiplexing. And multiplexing, basically the whole idea is that efficiently, how can you utilize the overall bandwidth of a particular channel, right? Now remember that bandwidth utilization is a huge topic, and there are so many different schemes that are available, so many different techniques that are there. So we cannot cover everything, right? So we will focus on only a few key concepts in this particular course. So first, let us try to understand the concept of multiplexing. So this term multiplexing in some other computer science courses also you might have come across. However, in computer networks, we are going to discuss about multiplexing in a little different way, right? So once again, multiplexing is about combining multiple signals into one signal. So we have a single medium, which is shared by multiple pairs of computers, and these pairs of computers, they want to use this use this common medium in a certain way, so that maximum data can be transmitted per unit time. That's the whole idea, right? So so how do we do it? So let us focus on this particular figure that you've seen in this slide in front of you, right? So let us look at this particular figure. So here, as you can see, that we have a link, right, which can be any link, right? So if we are talking about guided medium, it could be some cable that runs between the sender and the receiver. It could be a twisted pair cable, or it could be some other medium, or it could be even air as the medium, unguided medium, right? So we have some link, right? So let us try to have some abstraction that we have a sender, we have a receiver, and we have some link that runs between them. Now you see that it's not the same scenario that we have covered earlier. It's not one sender we are talking about or one receiver we are talking about. We are talking about, now let us try to understand this part, that we are talking about several senders, right? Several computers and several computers, several input computers, several output computers. Let us just forget about the computers and focus on lines. So we have several input lines, in input lines, and we have in output lines, right? We have one link. Now the question is that how can you make these computers, these links, connect with each other? So we have one link only, right? So these different multiple input links and multiple output links are basically connected through only one link. So for this, basically, that one link is going to be split into n channels, or in other words, think of it this way, that if you have n input links, in input lines, and if you have n output lines, these are going to be combined over this particular link to accommodate n channels. N channels are going to be there, right? So n channels are going to be there. So this process of combination and then splitting of these inputs to get the individual outputs, etc. This process is called multiplexing, demultiplexing. So you need a multiplexer which is going to multiplex the n input lines and send as kind of a single combined channel, single combined signal through the channel, conceptually like that. And then the demultiplexer basically tries to separate them out on the other end through certain mechanism, right? So how this multiplexing is going to be done and how this demultiplexing is going to be done is what we are going to understand shortly. So before we do and we look into the different ways in which this could be done, let us try to understand the taxonomical classification of multiplexing. These multiplexing techniques can be broadly classified into three primitive types. Number one, frequency division multiplexing. Number 2, wavelength division multiplexing. And number 3 is time division multiplexing. The first two, the frequency division and the wavelength division, have a lot of commonality between them, because so basically the frequency can be or rather the wavelength can be basically transformed to get the individual frequencies, right? So wavelength and frequency, these are interlinked. So frequency division multiplexing and wavelength division multiplexing have certain things in common. However, wavelength division multiplexing is typically talked about in the context of optical transmission, where the wavelength of a signal is very important, right? So then comes the time division multiplexing. So the first two are analog in nature, and the time division is typically used for digital transmissions. So let us now try to understand one by one how these things work. Number one is frequency division multiplexing, right? So n input lines, n output lines, and n channels in between. So frequency division multiplexing basically takes the link and divides the link into n channels. These n channels are basically logical in nature. So these are logical channels, and each channel can be allocated to each user, right? So every user is going to be allocated a separate channel. So this user can basically use the frequency range of that channel independent of the channels that are being used by the other users. So as you can see pictorially, even though these channels are basically logical separations, right? These basically, they do not overlap with each other. This is shown pictorially, but the question is that how do you make them separate from each other? So this can be done with the help of something called guard channels or guard band, right? So basically, the whole idea is that channel 1 and channel 2, for instance, can be separated with something called a guard band, right? So this guard band is kind of like a no man's land, right? Neither it belongs to country 1 nor it belongs to country 2. It's kind of a no man's land, right? So this is called the guard band, which basically separates channel 1 and channel 2. Likewise, channel 2 and channel 3 could also be, not could also be, should also be separated through these guard bands, right? So this is how this logical separation of the channels is done. And as I said before, that every channel is basically allotted to a user who needs to communicate from one point to another. So this separation is done with the help of multiplexing, and similarly, the demultiplexer basically has to take care of the reverse of multiplexing that is done. So let us try to understand a little deeper about how this frequency division multiplexing works. So, so here, as you can, again, let us directly focus on this particular figure. This is how this frequency division multiplexing is going to work. So let us say that we are talking about some baseband analog signals, right? So every source basically generates some baseband signals which are analog in nature, right? So these signals, they are put inside the multiplexer. So every, so this is line 1, so not line 1, this is yeah, so this is like input line 1, input line 2, input line 3 connected to different computers, and this each send these different signals. Now this multiplexer, what it is going to do, this multiplexer, it is going to modulate every signal, every input signal. It is going to first going to modulate the signal over a particular carrier frequency, okay, in this manner. So input signal 1 modulated over carrier frequency 1, input signal 2 modulated over carrier frequency 2, and the process continues. So now these modulated signals are then combined in a certain way. These, so let us say that this is the modulation process and you get these modulated signals, right? So this is your modulated signal. This is the second modulated signal. This is your third modulated signal. So these modulated signals are then combined in a certain way, right? And then it is sent out. This combination is basically what is done in multiplexing. So there is a multiplexer circuit which basically produces this combined, this is the one, please have a look. This is the combined composite modulated signal. Okay, so this is what the multiplexer does, right? So I hope that this part is clear to you. So now let us look at what the demultiplexer is going to do. So the demultiplexer is going to receive that modulated combined composite signal from the multiplexer, and then with the help of filters, first it is going to filter out the different signal components, and after this basically there is a demodulator circuit through the demodulation process. So the individual signals are going to be separated out, and only the carrier frequencies are going to be left out. So basically, what you are going to get is the input signals that were modulated are going to be demodulated out, leaving the carrier frequency separate. So I hope that this particular concept is clear to all of you. So you see the signal components that we had received individually, all these input signals, through this particular process, we are going to separate them out. Okay, and then they are going to be sent through the separate output lines. Is this clear? Now let us try to work on a particular problem which will slightly try to clear your understanding. So all of you, please look at this particular problem. I'm going to call names shortly and you will have to give me the answer. So everybody have a paper and pen handy with you. I'm going to give you a very simple problem to help you understand this frequency division multiplexing. Let us say that we have 5 channels. Each channel has 100 kilohertz bandwidth. So 5 channels, each channel has 100 kilohertz bandwidth. These are to be multiplexed together. Now the question that is asked is that what is the minimum bandwidth of the link if there is a need for a guard band of 10 kilohertz between the channels to prevent interference. Okay, so so let me give you half a minute. Simple arithmetic. Actually, many of you can do it mentally also. Very simple problem. So very quickly, we have very little time left. So please work on it and give me the answer. The question is that what is the minimum bandwidth of the link if there is a need for a guard band of 10 kilohertz? Anyone who has done it already?
Five 40 kilohertz.
540 kilohertz. Your name, please. Srijan has written 540. Prakash, very good. Who else has done? Pramit, Gaurav. See, there are many more exciting problems ahead of us. So please try to quickly do it. Don't spend too much of time. Anindo Sikdar. Anindo, what answer did you get? Sai Vamshi? Sai, can you hear me? Okay, so I think we have to move ahead in the interest of time. But I'm going to give you similar problems actually to work on, right? So I will give you question bank 1, and after that, after 2 days, we'll give you another question bank 2. Both of these question banks, if you do, then you will be all set in terms of your understanding of the concepts that are covered, right? So look at this particular figure, right? This is the answer, right? So this is 540, whoever has said is very right. So this is going to be like this. We have 5 channels, right? And as I said, every channel has a bandwidth of 100 kilohertz, like this, very simple. And there is a guard band separating these channels, right? So every guard band is going to be of 10 kilohertz, right? So how many guard bands will be required? 4 guard bands, right? So we have 5 channels, 1, 2, 3, 4, and 5. So between 5 channels, we can have 4 guard bands, right? So 4 guard bands will give you 40 kilohertz, and these 5 channels is going to give you 500 kilohertz. So 500 plus 40 is 540. 540 kilohertz is the correct answer. Very good. Let's now move ahead. The second concept, which is quite similar to what we have covered, is basically called wavelength division multiplexing, right? So conceptually, as if you are, you are doing exactly the same thing, but instead of the frequency, you are now playing with wavelengths, right? So you see that we have 3 different input lines with these signals, input signals of wavelengths lambda 1, lambda 2, lambda 3. So with the wavelength division multiplexer, you are going to produce a a composite signal where these 3 wavelengths are kind of like these are going to be combined into a signal of lambda 1 plus lambda 2 plus lambda 3 kind of composite signal, and then it is going to be demodulated and demultiplexed at the other end, and you are going to get the individual signals back, right? So here I think all of you know that frequency and wavelength, these are linked, right? So what is the, so from your basic physics, right? So what is the relation between wavelength and frequency? Who can tell from your +2 physics? Sorry. Yes, anyone? No one? Relation between frequency and wavelength?
Inversely proportional, sir.
Inversely proportional. So what is the formula?
Like frequency into wavelength equal to speed.
Yeah. Yes, right. So F equal to C by lambda, right? So this is typically, so again, like, so there are different variations, different types of consideration, etc. But as, you rightly said that these are inversely related. So you see that you can think of like combining these different signals of different frequencies like before, where the frequencies are going to be very high, right? So you need low wavelength pulses, right? So small wavelength. So small wavelength means like very high frequencies. So as if high frequencies are going to be all combined, right? So it's kind of like that. And so both of these, frequency division multiplexing as well as wavelength division multiplexing, are used for analog signals, right? Now let us talk about the other important multiplexing technique, which is called the time division multiplexing. Now in time division multiplexing, so that as if the time domain is divided into different parts, and each of these parts, which are called the slots, is going to be used by the users according to the assigned slots, right? So it is like this, that you have a shared channel. That channel is basically divided between the different users, right? So you have, let us say, we have 1, 2, 3, and 4 users, right? So these 4 users, their data are going to be multiplexed with the time division multiplexing technique, right? So you take the time domain and you put it, you split it up into different slots, and you assign each of these different input links to the different slots, and you kind of, you rotate this particular technique, right? So what happens is the data flow is going to be like this. First, first let us say that number 1 is going to have the slot, then the next time instant number 2 is going to have, number 3, number 4, and you repeat the process. So 1 2 3 and 4, 1 2 3 and 4, 1 2 3 and 4. So you repeat the process, right? So this is basically a conceptual way of assigning different time slots to the different stations. Okay, so this is called time division multiplexing. Now this time division multiplexing, conceptually all very good, as I said. Now how do you basically how can you execute this time division multiplexing? So one way of executing this time division multiplexing is through the technique called synchronous TDM, synchronous time division multiplexing. Now in synchronous time division multiplexing, it is like this, that so let us say that so there are different time slots, right? So this is station 1, this is station 2, this is station 3, which is utilizing 3 links, right? So this is for link A, link B, link C, let us say, right? So so it is going to be like this, that so for A, let us say that there are different frames that are going to come. So input frame A1, A2, A3. For B, B1, B2, B3, C1, C2, C3, right? Each of these basically is going to have the input duration, time duration for the frame of T units, right? T seconds, let us say, T seconds, T milliseconds, T microseconds, whatever you call T units, right? So the multiplexing is going to be done in such a way that finally you are going to have a frame which is going to have A1, B1, and C1 all put into one frame, right? All put into one frame in this manner. Now the question that is that these were like T units long, right? T time units long, T seconds long. However, if you are putting all of them, this should be 3T, right? So T plus T plus T. So it should be like this, but it is not, right? So here the whole idea is that if you want to adopt this kind of technique, then you have to increase the data rate of the link 3 times. N times you have to increase the data rate of the link. So if you increase the data rate N times, what is going to happen? The unit duration is going to be N times shorter. So this is going to become T by 3. This is going to become T by 3, and this is going to become T by 3. So T by 3 plus T by 3 plus T by 3. These 3 time durations corresponding to each of these different frames, because the speed has been increased in times, 3 times in this particular example, you are going to put them all, combine them all together into one frame. So you have one frame, second frame, third frame, where the individual frame durations have been cut to 1/3 of the original frame duration. So each frame in this example is going to be 3 time units, and each time slot is going to be of duration T by 3 seconds. Okay, so this is synchronous time division multiplexing. Now there is another type of multiplexing which is called statistical time division multiplexing. Now the problem with synchronous time division multiplexing is that if you have empty slots, right? If you have empty slots, what is going to happen? So let us say that you have something like this. So here actually you did not have any empty slots. So every slot was occupied by one frame from each of these different lines. Now this sort of technique, it works very well. But if you have a situation like this, where A1 is present, but there is no A2 and A3. There is B1 and B2, but no B3. For line C, there is no C1, C2, C3. Here you have D1 and D2 but no D3. Here you have E1 but no E2. You have E2 but no E1 and E3. So if you want to do synchronous time division multiplexing in the way I mentioned, the net result is going to be that you are going to have these different frames in this way. You are going to have A1, B1, and for C there is nothing. So there will be an empty slot. Then you will have D1 and another empty slot. So this is for one frame. For the second frame, also you will start with an empty slot, B2 empty, D2 and E2 in this manner, right? So you see the problem is that in computer networks, many times you have bursty traffic, right? So you really do not have all the links occupied at all times, right? You do not have all the links occupied at all times. So if you have such a scenario, so these slots are going to go waste, which will lead to underutilization of the link. So that is where statistical time division multiplexing comes as a solution, where the whole idea is do not leave any empty slot, where the whole idea is that you do not leave any empty slot. So how is it done? It is done like this, that every frame is going to be accompanied by its header. So A1 is going to be accompanied with its header, B1 is going to be accompanied by its header, D1 is going to be accompanied by its header. So note over here that there was no C1 over here. So you see that there is no empty slot corresponding to C, like in the case of like in the case of synchronous TDM. So in the case of this synchronous TDM, there was an empty slot that was left out because line C did not have any frame to send. But over here, we do not have so. So A1, B1, and there is no C1. There is no empty slot for C1. So rather, the slot is occupied by D1. Now the question is that how do you know whether this frame belongs to D or to C? Or how do you know this one belongs to B or to C? So like that you do not know, right? So for that, the proposition is that you use a small header, small a, small b, and small d correspond to small headers corresponding to which line it belongs, this particular frame belongs. And so now you might think like, so although it solves the problem of empty slot and inefficiency as encountered in synchronous TDM for certain types of traffic, but how does it solve the problem overall? Because you are introducing some headers. Now these headers basically, although these are like small headers that are these are additional headers that are introduced, these headers are basically small in size. These are like very small headers, 1 bit, typically 1 bit or 2 bits long, very small headers. So these small headers basically they do not occupy too much of space. Rather, so these can help in identifying the different frames that are associated with them. So that's the statistical time division multiplexing. So the statistical time division multiplexer basically checks each input line in a round robin fashion, and then it allocates a slot for each input line if the line has data to send. Otherwise, it skips the line and checks the next line. Okay. So let us quickly work on a problem involving time division multiplexing. Okay. So let us say that so let us say that we have a scenario like this. The data rate of each input connection is 1 kbps, right? So each of these inputs have 1 kbps connection. If 1 bit at a time is multiplexed, right? So these are like 1 bit longs, right? So 1 bit at a time is multiplexed. What is the duration of each input slot? Number 1. Number 2 is each output slot, and the number 3 is each frame. What is the duration after multiplexing? Very easy. Please tell quickly. Prakash, this time, can you tell?
Doing, sir, not yet done.
No, no, mentally only you can do. Very easy. Anyone who has done? We are running out of time.
One
Let me show
frame
you
is
the
1
solution.
millisecond, I guess.
Very good, very
1
good,
by 3.
very good. Who? Prakash, right? Who? What is your name?
Satprakash.
Yeah. So every time actually you tell your name, because I'm not able to see your face if I switch to the screen mode, right? Okay. So let me show you the solution, right? So guys, please work on these problems yourselves, right? So I'm going a little fast, so I'm not able to give you too much of time, but you make sure that you solve on these independently in your hostels. So the data rate is given to be 1 kbps for each input, right? So that means that the bit duration, so bit duration means the time for every bit is going to be how much? 1 by 1000 second, and 1 by 1000 is 1 millisecond. Clear? So this is how you get the duration of the input time slot to be 1 millisecond. So this is your bit duration. Now the second question was what? Each output slot, duration of each output slot. So if 1/3 of the slot is occupied, right? So input time slot is what? 1 millisecond. So the output, the duration of the output time slot is going to be 1/3 millisecond, right? Now you are putting them all in the form of frames. So what about the frame? So it is going to be 1/3 into 1/3 into 3, 1/3 plus 1/3 plus 1/3, 1/3 into 3, which is going to be 1 millisecond again. So the duration of the frame is the same as the duration of the input unit. Okay. So there is something also called space division multiplexing and code division multiplexing, which we are not going to cover over here, but that doesn't mean that these are not important. These are simply out of the syllabus of this particular course. But when you go for wireless communications like 5G, 6G, etc. So space division multiplexing, basically cellular communication, space division multiplexing is a very important concept, right? Because actually there you are talking about that, spatially how you are going to separate your antennas so that so adequate levels of multiplexing can be achieved. So there is something called MIMO communication, multiple input, multiple output. So MIMO communication, you can achieve with the help of space division multiplexing, right? So this is space division multiplexing, so that you do not, if somebody tells you space division multiplexing sometimes, so that you do not feel yourself to be lost or puzzled. I just wanted to tell you that there is something called space division multiplexing. Likewise, there is something called code division multiplexing. Here, actually, this is something that all of you have you have heard about it, because you have heard about CDMA, right? So CDMA uses this type of multiplexing technique, which is called code division multiplexing, right? So CDMA, all these CDMA phones, etc. So CDMA based wireless communication basically uses code division multiplexing, right? But again, this is out of the syllabus of this course. So in code division multiplexing, there are unique codes that are generated, right? So these codes basically are assigned to every station. So every station will be assigned to a particular code. These codes are called chips. So these chips are basically these are going to be used. Okay. And these signals are going to travel with these codes independently. Okay, so with this I'm going to stop over here, and tomorrow we are going to continue from this point on. So thank you, students. Actually, there is one of my students PhD defense that is coming up at 12 o'clock, so I need to quickly end this, and we'll catch up tomorrow again. Thank you. Bye.